I am Anil Kumar Khandelwal. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll consider a very important concept about what happens with limits at infinity. When we say at infinity, it's kind of wrong. The actual thing is limits when x approaches infinity. So that's very kind of important to understand. Here are six questions which we'll answer one by one. This will lay a foundation for our upcoming concepts on limits, where x will be approaching positive infinity or negative infinity. So let's start with the very basics. In case you want to learn directly from me, feel free to send an email on globalmathinstitute@gmail.com. Our students are right there on the top, getting the best marks. So, as you see, we have written limit pi over x to the power of 2n, where n belongs to natural numbers and where x approaches infinity. So, let's understand this term. When we say x approaches, means when x is very, very large value, right? Not at infinity, correct? You cannot be at infinity. So, when x is very, very large value. Many times, if you don't know how to solve that question, in that case, you can actually substitute relatively a large number for x and see what value you get. Round that decimal number to a whole number if you do get one, right? So basically, what we are going to see here is when x approaches infinity, what happens to the y value? If y value approaches some value, let's say L, in that case, we'll have a horizontal asymptote, which will be y equals to L. So, working on this kind of a limit also helps us to figure out what is the horizontal asymptote for the given function. And that is a major application where you will see such use of infinity, approaching infinity. Great. So let's begin with the very first one and understand the concept, which is limit x approaches infinity. So we are taking positive infinity here, where the function is pi over x to the power of 2n, where n belongs to natural numbers, means n can be 1, 2, 3, 4, any number, right? So basically, we are saying that the denominator has an even power. So that is what we mean, right? So this really means what? It means that the denominator is even power. Correct. And pi, is a constant, right? Pi is a constant. So pi or any other constant could have been there in the numerator. For such functions where we have even power of x, what happens? And that too in the denominator. So clearly, when x approaches infinity, this function you can see will approach. So we could write y equals to here, right? So some value y which we are looking at. So we can say y approaches 0, right? Because any constant divided by a large number will give you 0, right? So that's what it is. So you say 1 divided by infinity is 0, but not exactly. You cannot divide by 0. That's an indeterminate. But when you are approaching division by a very large number, you are approaching 0. You're not at 0. So that's what it means. So here we have y approaches 0. On a graph, how does it look like? Let's have a look at that also, right? So, since everything is positive here, you can see x to the power of 2n. So, even if x is a negative value, when the power is even, it makes it positive, right? So what we have here, and in this particular case, we are approaching a value which is infinitely large on the positive side, on this side. So it is going to be positive, right? So basically, the function is going to approach like this. So this is how it is approaching infinity, correct? So that is how I've shown you on the right side where x is approaching a large value, infinitely large value, correct? So I hope graphically also it is clear. Well, if I sketch the same thing for what happens when x approaches negative infinity, in that case also you see it's a replica of this reflection on the y-axis, and the graph will be kind of like this. It still approaches zero, and both approaches from the top, right? So that's how it will look like if we have even degree for x in the denominator, right? Now, let's take up the next one, which is for an odd degree, correct? So, of course, even an odd degree, there will be slight difference. So, let's look into this. So, we are now trying to calculate limit when x approaches. We have taken positive infinity this time also, 2 over. So, 2 is a constant, x to the power of 2n plus 1. Odd, right? When x is approaching positive infinity, in this case also dividing by a large number will actually give you 0. Now, since it is positive and you are approaching from above, we normally write this as 0 plus. Now, that means approaching from above. Many times you have to explain how are you approaching this particular asymptote. So this is your horizontal asymptote in this particular case. So let me write down, we have a horizontal asymptote which is y equals to 0, and you are approaching from above, right? On a graph, if you want to reflect the same situation as we did last time, here also on the right side you are approaching kind of like this, right? So that is the part which you just seen. However, if x is negative, right, and you're approaching negative infinity, means if you're approaching on this side, then this function will be negative, right? Since the power is odd. So you will approach like this, right? It's kind of 1 over x kind of a graph, right? So that will be here. But you see, x is approaching from above, y is approaching from above when x is approaching positive infinity. Correct? So in short, when x approaches infinity, then y approaches 0 from above in this particular case, where we are considering positive infinity. Now let's take up the next example. So now we have to figure out what is the limit when x approaches negative infinity this time, and we have a function which is x over square root of x squared. Now, square root of x squared, it is always positive, right? So that means the denominator is positive. So the numerator will be minus infinity means a negative number. So, so what will happen to this particular function? So let me rewrite this as what is limit when x approaches minus infinity for the given function, which here is x over. Now, what is square root of x squared? Since it is always positive, you cannot write this as x. It has to be absolute value of x. You get the idea? It has to be absolute value of x, because that square root of x squared is going to be positive no matter whether x value is negative or positive. You get the whole idea. So it is positive value, right? So that's what it is. Now, when we are looking at x, which is less than 0, right, approaching in minus infinity, then absolute value of x will actually be negative x, correct? Because that's how it is. It makes negative as positive. So when you have negative value, it makes negative negative as positive. And therefore, you could rewrite this as limit x approaches negative infinity. And here you get x over negative x. Now, when you divide x with negative x, you get negative 1, right? So we have limit x approaches negative infinity of negative 1. Now, negative 1 is a constant. So that means it will remain negative 1, right? It is approaching negative 1. Now, since negative 1 is a real number, we can say here that we have a horizontal asymptote, which is y equals to negative 1. Do you see that? Now it's important to understand that it was an absolute value function, which we wrote as negative 1 since we were approaching negative infinity. Okay, and so we got a value which is minus x. You get the whole idea, right? So that is how it is. Now we are approaching x with this kind of a function, negative value, negative 1, right? So that's what it is. Now in case you put a value here, then if you see how it really approach, it is a horizontal line approach, right? So here the horizontal asymptote is y equals to negative 1, correct? You can also draw this kind of line like this, and it's actually minus 1 on this side. So the function is not defined at 0. So if you see the function, it is not defined at 0. It is kind of like this, right? And on the right side also, it is if you define the function. So that is what this function is, x over absolute value of x squared. Well, in this case, whether you approach negative infinity or you're on the negative side, the value of the function is negative 1, right? So you are at negative 1. You see that? So that is the diagram for the function. And from there, it is very clear that as you approach on the negative side, you are at negative 1 for all values, right? So that is going to be y equals to minus 1. So, strictly speaking, y equals to minus 1 in this case is not the value approached, right? Is not the value of y. It is the value of the function, correct? So we should not be saying that y equals to minus 1 is a horizontal asymptote. So we kind of remove that part and say y is equal to minus 1 as x is approaching negative infinity, right? You get there, it is minus 1, correct? So that's what we will say. I hope that concept is clear, right? Normally it will be horizontal asymptote, but here you can see it is this value, right? So it is already at this value, correct? So that is how we'll say y equals to minus 1. Okay. Now let's take up the next example, which is the rational function of the kind ax plus b over cx plus d, where a and b are real numbers, and once again we have x approaching minus infinity. So let's write down the function. We have limit x approaches negative infinity, and the function is ax plus b over cx plus d. So whenever you have this kind of a function, here what you note here is that in this rational function, degree of numerator and that of denominator is same. So what you do is, to simplify, you take x common. So this process can be applied to all questions of this type, right? So I could even write x to the power of m, you understand, and the same power m. You get the whole idea. If this is same, so in that case, I can write here x to the power of m as a common thing. So I can change this and show you what happens when I make it kind of same denominator, exponents for both numerator and denominator, right? So same power x to the power of m taken outside, we have a plus b over x to the power of m. And here we have x to the power of m, and we have c plus d over x to the power of m. Perfect. Now in this particular case, you can see the same powers of m, x, they get cancelled out. So whether it was x to the power of 1, or I could have changed the question to m degree, the same degrees of numerator and denominator. What you get is this, right? So now you can see that as x approaches negative infinity, anything with x in the denominator also approaches 0, right? So whether it is b or it is d, right, any constant to the of this form will approach 0. So these two terms, they are approaching 0, right? So we can like kind of take them off. So we are left with a over c. So we are approaching a real value a over c. So in this particular case, that becomes the limit of the function as x approaches negative infinity, right? So, so as x approaches negative infinity, we can write down here that horizontal asymptote is y equals to a over c. So a over c is the ratio of leading coefficients when the degree of numerator and denominator of a rational function, like given here, is same. Right, perfect. So let's now take up the next question, which is where we have the degree of numerator one higher than that of the denominator, right? So let me write down the question here first. Limit x approaches, well, minus infinity, and we have ax squared plus b over cx plus d. Now, in this case, what you see is that we can take x squared common, right? That's the highest power. We can limit x approaches minus infinity, x squared common, we get a plus b over x squared. And the denominator, we can take x common, right? And we get c plus d over x. Well, so if I would have taken x squared, then be c over x squared, right? But x will work. So now what happens is you can cancel these, and you're left with limit x approaches negative infinity. And we also saw that these terms will approach 0, right? So we are left with that. And one of the x cancels, so one of the x cancels. So we are left with uh, x times a over c. So you see the difference in this and the previous one. Here we have x in the numerator, right? So if x approaches negative infinity, the y value will also approach negative infinity, right? So in this case, we do not have any horizontal asymptote. We say that the y value or the limit, we can write here, limit approaches negative infinity, which is not a real number, right? So in this case, we do not have any horizontal asymptote, so no horizontal asymptote. Right? In fact, y equals to minus x. In this case, x will be oblique asymptote. So this is a case of an oblique asymptote. So we are writing here oblique asymptote. However, we are not going there. It approaches a line y equals to x. You can see, right? So x is what it is approaching, right? As x approaches minus infinity. Now, depending on the values of a and c, it could be approaching the line y equals to x from above or from below. That's a different story. However, we see in this particular case that we have an oblique asymptote, not an horizontal asymptote. Okay. Now let's take up the last question, which is kind of tricky. So in this question, which is limit x approaches, we have taken minus infinity square root of x squared plus x plus x, right? So if I substitute minus infinity here, we get kind of what? We get the infinity minus infinity case, right? This is also an indeterminate. You cannot really find its value. You are subtracting one infinity from the other, right? We don't know what really happens in such a case. So we call it indeterminate. Now, really, how do we answer this question? Is let us rationalize this, right? So if I rationalize, what do I get? Limit x approaches minus infinity. So wherever you see this radical and you get indeterminate case, in that case, rationalization helps. So rationalization means what? Multiplying and dividing by the conjugate, right? So in this case, conjugate is what? So let me write in a different ink. It is square root of x squared plus x minus x, right? Divide by square root of x squared plus x minus x. So that becomes the conjugate. So we are multiplying and dividing by the same number, which is multiplying dividing by 1. So it does not really change the equation, right? So it is still the same. However, it helps us to answer the problem, right? So now what happens? So now let's rewrite this as limit x approaches minus infinity. The numerator a plus b times a minus b, you can see becomes a square minus b square. So what we get here is x squared plus x minus x squared, right, over. We have this term here, which is uh, square root of x squared plus x minus x, right? Now, in the numerator, x squared and x squared cancel. We have limit x approaches minus infinity, and here we have x in the numerator. In the denominator, what happens? How do we simplify this denominator? We have x squared plus x minus x, right? What we can do is that we can factor out x squared, right? So here is a simple technique to understand, very critical though. X squared we are taking common between x squared plus x. So we are left with 1 plus 1 over x, right? X divided by x squared will be 1 over x, correct? Minus x, right? Now, as x approaches negative or positive infinity, 1 over x will approach 0. So you are left with square root of x squared. You see that? You are left with square root of x squared. So in the denominator, we have now square root of x squared. Let me squeeze this in. Limit x approaches minus infinity, x over. This becomes absolute value of x minus x. You see that? So we have square root of x squared, which is absolute value of x, as we have seen in an earlier example. That is how we write square root of x squared. Now, since you are approaching minus infinity, that absolute value of x should be what? It should be minus x, right? So we can rewrite this question as limit x approaches minus infinity, and we have x over minus x minus x. You see that? So it is minus 2x, right? So we have limit x approaches minus infinity, x over minus 2x, x and x now cancel, and we get answer as minus half. See, we got a real value, correct? Minus half. And therefore, we can now write that the horizontal asymptote is y equals to minus half. Do you see? Very important critical question from test point of view, right? So that is how we answer such questions based on limits. So you see, sometimes when we're talking about approaching infinity, we are seeing that the function actually settles down. Do you see that? As x grows without bound, some functions they explode, which we saw with oblique asymptote, right? And the others balance out. Horizontal asymptotes reveal that balance. So that's a figurative way of looking at it. I hope the concept is absolutely clear. Feel free to write your comments, share your views. I'm also releasing a book on calculus. You can always buy my book, which will be there on Amazon. Those of you who want to have a sneak peek in this book may send an email to me. Also, I encourage you to watch more videos in this playlist and some lessons which I've had with Amy. They may help. Thanks for a wonderful day and all the best.